Now that we've defined the different type of variable, let's now see how you can better summarize those variables, or how you can compute key statistics that will give you an overview or a summary of your data set. So there are different type of summary applied to the different type of variable that you've seen. So first of all, you have the summary statistic for quantitative variable, but also the summary statistic for qualitative variable. Talking about the summary statistic of the quantitative variable, you have what you call central tendency characteristics, but also variability and dispersion statistics. So central tendency characteristics are key statistics such as the mode, the mean, or the quantile that give you an overview of your data set, that give you some summary of the information contained in your data set. So the mode, for instance, is the most frequently occurring value of a variable in the data set. Right, so let's for instance consider the example of the number of housemates per MPP student. So let's say most students answer they have 2 housemates, so therefore we will say that the mode of the variable number of housemates of MPP student is 2. You also have the arithmetic mean or the average. So most of the time we will simplify by assimilating the arithmetic mean to the average, and is computed by adding up the value of the data and divide by the total number of observation. There are other type of average as well, be it less used, the geometric and the harmonic. So most of the time when we will talk about the average, it will imply we are talking about the arithmetic average or the arithmetic mean, and it's given by, as I said, you remember the sigma sign or the Greek value letter that we use when we were talking about basic math for stats. So this is something that you always come across a lot during this lecture and this course of data science. So it's read, remember, has the sum of xi, so x at the subscript I to the subscript n, and you divide this number by the total number of observation, and then you have the arithmetic mean, right? So you also have quantile. Quantile is any of several ways of dividing the total number of observation into equally sized group. It means each group have the same number of observation. For instance, you have the percentile. It divides the data into 100 equally sized group. You also have the quintile, which divide the data into 5 equally sized group, and the quartile, which divide the data into 4 equally sized group. The most widely used quantile is the median. So it means it divides the population or the data set into 2 equally sized groups in such a way that half of the observation, or 50%, are smaller than this specific value of the median, and the other half is greater. And the median is also called the second quartile or the 50th percentile. And if in terms of comparison on when do we use the median or when do we use the mean as a summary statistics, it's better to use the median when you have less outlier. So the median is said to be more robust to outlier than the mean, than the average, right? So that's something very important. You also have the other quartile, namely the 25th percentile or the first quartile, and the 75th percentile or the third quartile. So it's also important because it tells you the number of observations. So it's the value of the data set in such a way that 25% for the first quartile or 75% for the third quartile of observation lies below this value. So it's also very important to describe your data. For instance, we can find out that considering our example of the number of housemates per MPP student, that the first quartile is 1. It means that 25% of students of MPP student has said that they have less than 1 housemate. And then the same example can be taken for the third quartile. However, the average or any of the quantile do not tell us anything about the variability on the data. It means, remember, these are central tendency characteristics. So if you would like to get a sense of the spread or the variability of our data, we should go for the standard deviation, right? And then remember the word standard deviation. So we will try and see. So here the idea is to try to get a sense of how much each observation deviates from the mean. So the deviation from the mean. So I'm subtracting each of my observation by the value of the mean. And here one of the first idea that can come in mind when you would like to compute the standard deviation is that you will try and subtract each observation by its mean and sum that up, but unfortunately it's equal to 0. Right, and I give you a little hint here, and I would like you to go back home and do this homework and show me how, when you want to compute the standard deviation, has the sum of all observations deviate from the mean, you get 0. So you should be able to tell me why, and I give you a hint here. So using the different basic mate property that I show you above, you should be able to compute this value. So that's the reason, because this figures sum up to 0, brilliant mathematicians come up with another solution. So instead of summing up the deviation from the mean, they sum up the square of the deviation from the mean and they take the square root. Remember, this sign is the square root, right? So this is how we compute the standard deviation, and this formula has to be memorized because it will be widely used in the coming lecture, right? So, and remember, we are trying to compute a dispersion or a variability statistics, and a high standard deviation means the data are far or less concentrated around the mean, because we are measuring the deviation from the mean, how much each observation deviates from the mean. This is what we call standard deviation, and tomorrow during the tutorial you will practice those formula. So apart from the standard deviation, you also have the interquartile range. The interquartile range is the difference between the first quartile and the third quartile. Here, for instance, so the interquartile range is also widely used when you have less outlier. So it is a good measure of the spread of your of the variability in your data set in the presence of outliers. So it's better to go for the interquartile range when you have more outlier than the median. So it's much more robust. It's like the median is for the average for central tendency characteristics. So what is an outlier? We are talking a lot about outlier, but you should already get an intuition. We are talking about outliers. They lie out of the data set. Outlier, I'm lying out of the data set. It means these are not plausible values. These are values that are not close to the reality. As an example, we consider the number of housemates of MPP students. So I'm asking each of the MPP students to tell me with how many housemates does he live with. So some students will say, okay, I have 0 housemates. It means they are wealthier enough to afford a single house in Maastricht. Other will say I have 2 housemates. Other will say I have 3 housemates. Other will say I only have 1, or other will say I have 20 housemates. For those who can really not afford the housing prices in Maastricht, which are becoming higher and higher, right? So those you will guess that people who will say they have 20 housemates is not a plausible value. So it's an outlier. So it's not something which is close to the reality. And generally, when you have quantitative variable or continuous variable or even discrete variable, in order for you to depict or to observe whether you have an outlier in your data set, you use a box plot. So this figure here is a box plot. The box plot show you the different quantile. So you have the minimum, you have the lower quartile, so the 25%, you have the median, you have the upper quartile, you have the maximum, and then you have the outlier. And I will show you how to statistically define or statistically identify an outlier. Right? And here is another figure where you can clearly see. So here you have the interquartile range, you have the average, you have the median. Remember, these are central tendency characteristics. The interquartile range is a spread and variability characteristics, right? And how do you know that a specific value of an observation is an outlier? This is what we are going to do here. Here I consider the example of your data set. So I took the income variable, which is a continuous variable from the Kyrgyzstan Integrated Household Survey, and I plotted the income. Here you can see when I plotted the income that we have 3 outliers. Right? But why are those observations, and what is the value of those observations, and what is the value of the lower whisker and the upper whisker in this data set? How do we detect the outlier? So here I did a summarize of the variable income and I use the detail option that you will see tomorrow during the tutorial. And here you can see the different quartile. You have the first quartile, which is 50,290. You have the median or the second quartile, which is 72,340.5, and you have the third quartile, which is 107,946. You also have the minimum of the data set, which is 2,342, and the maximum of the data set, which is 50,066. So you also have the standard deviation. So here, let's try and compute each of the value or identify the lower whisker, the upper whisker, and the outlier. So first of all, from the summary statistic, as I see, we have the first quartile or the 25th percentile and the third quartile or the 75th percentile. So here again, I gave the value already. So the interquartile range is the difference between the third quartile and the first quartile, which is here 57,656, right? Now if we would like to compute the lower bound for observation that are not outliers, so the limit that if you are below this value you are considered as being an outlier, right? We take the lower quartile or the first quartile and we remove 1.5 of the interquartile range, and what we have here is minus 36,194, right? This is what we have. And here you can see that the minimum of the data being 2,342 is not an outlier because this value is not lower than this value. So the lower whisker extend at the minimum, and that's what we see here. So here you see this value, which is the lower whisker, is not an outlier and it's the minimum of the data. So having said that, you also have the upper bound, or the, if you want, you take the upper bound and you do the 1.5 times the interquartile range, and you have a value to be able to determine the upper whisker. The upper whisker here being this value that we try to know the exact value, because in this figure we cannot clearly see. And each observation that will be above the upper whisker will be considered as an outlier. So what is the value of the upper whisker? So this value is 194,430, and the maximum of our data being 500,066 is an outlier. So the upper whisker cannot extend here, but we stop at a specific value of our data, which is right below this value, because this value is not part of our data set. So the upper whisker will extend to 191,594, which is the largest observation, which is not an outlier. So that's very important to understand. So this is how you identify the outlier. You always take 1.5 times the interquartile range that you remove to the first quartile, or you add to the third quartile to be able to have the upper and the lower whisker. So now, having talked about the summary of each quantitative variable, now let's see the relationship between two quantitative variables. So if you would like to appreciate how two variables are moving together, you should compute two measures. You have the covariance and the correlation. So the covariance informs you on the tendency of two variables to move together linearly. I want to point the fact that this is linearly, because you can have a covariance which is equal to 0, but it doesn't mean there is no relationship between this variable, but rather that there is no linear relationship between those two variables. And the formula of the covariance is given by 1 divided by n minus 1. Sigma, always you see this Greek letter is always coming back, and then you do xi minus x bar times yi minus y bar, where x bar and y bar are the average of each of those variables. Right? Let's say for instance you want to see the relationship between the income at the household and the expenditure. So you want to see how much people tend to spend as their income increase. So one of the guesses that you will have is that the more income you have, the more expenses you are going to have. So it means that if we compute those two variables, we will expect a positive sign of the covariance. And here a positive covariance implies that the two variables x and y tend to move together, so both up or down at the same time. So I just took the example when x is considered as being the income and y is considered as being the expenditure, right? It means that if the income increase, then the expenditure will increase, or if the income decrease, then the expenditure will also decrease. So the same thing, the negative covariance implies that the two variables x and y tend to move together. So when one is going up, the other is going down, or the other way around. So here the covariance only informs us on the sign of the dependency between x and y. It doesn't tell us anything about the strength of the relationship between the two variables, but the correlation coefficient does. So the correlation coefficient is obtained by dividing the covariance by the product of the standard deviation of the two variables. So you have the covariance of x and y that you divide by the standard deviation of x times the standard deviation of y. This is how you obtain the correlation coefficient, and it gives you the strength. So the strength, how strong they are. So if you have the correlation which is between -1 and 1, so again it's always between -1 and 1. It cannot be above or below that. And it is worthwhile to mention that when you have a 0, so the closer the correlation coefficient is to 1, it means the relationship, the linear relationship, is strong, right? So this is very important to know how to interpret. So if you have a correlation coefficient which is close to 1, it means the relationship between x and y is strong enough. And if it's close to 0, it means the linear relationship between x and y is not strong enough. And I'm insisting in the term linear because a 0 coefficient of correlation doesn't necessarily imply that there is no relationship between the two variables, but that the relationship might not be linear. This is very important for you guys to understand.